All right, so now we're going to look at the same type of problem that we looked at in the past, where we've got two blocks that are connected by a rope, and we are asked to determine basically how fast the blocks are moving right before the hanging block hits the ground. But in this case, we are now going to consider the fact that there is friction present. So the first thing we should do is figure out how much friction there is acting on the larger block. So if I were to draw the forces that are acting on the block, I have a normal force acting because it is in contact with the surface. I have the weight of the block, or the force of gravity, acting down. And now I would have friction acting on the block as well. Now we know that the frictional force is just the coefficient of friction times the normal force. And in our particular case, since the block is only going to move along the horizontal or the x direction, the sum of the forces on the larger block along the y direction has to equal 0. So I have the normal force acting up, and then I have the weight of that block acting down. And we know the mass of the block is 2 kilograms. So this would be 2 kilograms times 9.8 meters per second squared. So the normal force is just 19.6 newtons. Once we know the normal force, we can figure out the amount of friction because we know the coefficient of friction is 0.4, and then multiplying it by the normal force, we get that the frictional force is 7.84 newtons. Now, we're going to use the concept of work energy, and in this particular case, we're going to consider both blocks as our system. And if we consider both blocks as our system, then we don't have to worry about the tension because that would be internal, and there is no work that is being done by the tension. Well, okay, let me back up. So there is work being done by the tension, but there's positive work being done by the tension on the big mass, and there would be negative work being done by the tension from the little mass. And so essentially those cancel out because those are internal. So the sum of the tension acting on our system would end up being 0. So we don't have to worry about that because essentially it's an internal force. So if we consider both blocks as our system, we want to look at the work energy theorem, which says that the net amount of work done by non-conservative forces is just equal to the change in energy. So the final energy, which is the sum of the kinetic energy plus the potential energy, minus the initial energy, which is again the sum of the kinetic energy plus the potential energy. So the only non-conservative force here that is doing work is the frictional force, and the work done by friction is just minus the frictional force times the displacement. The smaller block is going to fall through some distance here of 2 meters, and therefore the top block is going to move through a distance of 2 meters. So the frictional force acts over that 2 meters, so the work done by friction is going to be the frictional force times the displacement of 2 meters. So the work done by friction is just minus 15.68 joules. Now, you may recall that that negative sign there is because the angle between the frictional force and the displacement is 180 degrees, and cosine of 180 degrees is just minus 1. So we always have the fact that the work done by friction is just minus the frictional force times the displacement. So now that we have the amount of work done by non-conservative forces, we can plug that value in, and we can add all of the terms that we have in terms of kinetic energy and potential energy. So I'm going to just write it all out first. So the work done by non-conservative forces would be equal to the final kinetic energy, and this would be the kinetic energy of both masses together because they travel together at the same time. They're always going at the same speed, plus the final potential energy of each block. So I would have the mass that's sitting on the table, and then I would also have gravitational potential energy from the mass that's hanging. And then that's minus the kinetic energy initial. And again, they initially have some velocity together. And in this case, they start from rest. And then each might have potential energy initial. So many of these terms can cancel out because the block starts from rest, so the initial velocity of the whole system is 0, so that term cancels. Additionally, the potential energy of the block that's sitting on the surface doesn't change. It has the same initial position as it has the final position vertically, so that cancels out. And then in our picture, we can take the lowest position here to be 0. So then our hanging mass starts off at a height of 2 meters, and when it gets to the ground, right before it hits the ground, it has 0 vertical position. So that means that the final potential energy of the hanging mass is also 0. So now I can plug some values in, and I can see if I can determine the final speed of this system when friction is acting. So the non-conservative force here would be friction, and it does work of negative 15.68 joules, and that has to equal 1/2 the combined mass of the system, which is 2 kilograms plus 1 kilogram, so that's 3 kilograms. And then all of those terms are 0, and then I have minus the initial potential energy of the hanging mass. Its mass is 1 kilogram times gravity times the height that it starts off at, which is 2 meters. So I can calculate what the initial potential energy is of the hanging mass, and that ends up being 19.6 joules. And I can add 19.6 to both sides, and when I do, on the left side I get 3.92. And now I can divide both sides by 1.5, and I get 2.61. And then finally, I can take the square root, and I get that the final speed is 1.62 meters per second. And that's the final speed of both masses right before the hanging mass reaches the ground. Now, on a previous video, we looked at the situation where there was no friction, and under that circumstance, the final speed was 3.61. So it's not going as fast because friction is actually opposing the motion. The other part to this question is asking us to determine the tension in the rope for the case when there's friction. And so in order to do that, we have to realize that we have to just focus on one of the masses. And so previously we focused on the larger mass that's sitting on the surface, and we use that to calculate the tension. But this time we'll do it a little different, and we'll focus on the smaller mass. So if we focus on the smaller mass and not the system of masses, then the tension that's acting on the mass is actually external to the system, and there is work done on that smaller mass. So we can use the work energy theorem, which says that the work done by non-conservative forces acting on the hanging mass would be the kinetic energy final of that mass plus the potential energy final minus the initial energy, which would be the kinetic energy initial plus the potential energy of the hanging mass initially. So as with the other case, there's things that cancel. So the initial velocity is 0, and the final position of the mass is right before it hits the ground, and so that is also 0. The only force that's actually doing work here, the only non-conservative force that's doing work, is the tension. So we know that work done by a constant force is just the force times the displacement times cosine of the angle. And so for tension, this would be, the force would be the tension, the displacement, and then cosine of the angle has to equal 1/2 the mass that's hanging times the final speed squared, which we know, and then minus mgy initial. So from the previous example, we found that right before it hits the ground, when there's friction acting, that the speed is 1.62, right before it hits the ground. All right, so we need to ask ourselves, what is the angle for the tension? And so the tension is acting upward, but the displacement of the mass is downward. And so the angle between them is 180 degrees, meaning that the tension is actually opposing the motion for the hanging mass. So this would be the tension. The displacement is how far the mass falls, which is 2 meters, times cosine of 180 degrees, equals the final kinetic energy, which is 1/2 the mass, which is 1 kilogram. And right before it hits the ground is traveling at 1.62 meters per second. And then minus the initial potential energy of the mass, which is 1 kilogram times 9.8, times the height, which is 2 meters. So I can do some calculations here. I'm going to get the tension times 2 meters, cosine of 180 is -1. The kinetic energy term here for the hanging mass right before it hits the ground is 1.32 joules. The potential energy that it has to start with is 19.6. I can combine those terms and I get negative 18.288 joules. And then I can divide both sides by -2 meters, and I get that the tension in this case is 9.14 newtons. So the tension here is also higher when there's friction present than what it was earlier without the friction. So keep in mind that when you have problems where you have masses that are attached, if you consider both masses as your system and you use the concept of work and energy, then the tension is not going to be included in the work done by non-conservative forces because it's internal and essentially it's doing positive work on one object, negative work on the other. But when you want to find the tension, you have to isolate one of those masses and look at the work that's done by non-conservative forces on that single mass. And this is similar to what we did with Newton's laws of motion. If we wanted to find the tension, we had to look at a single mass.